Additional little thing that I want to describe about this sigmoid function is as follows. So as we saw in this slide, we know that this guy is more intuitive form to understand, right? In terms of the competition between e to the power of y and e to the power of 0, right? But why do we use this form as our sigmoid function, right? So this is because of some computational efficiency. So if we just program or implement our sigmoid function in this form, okay, and then we would have to compute e to the power of y twice because they are both appearing both in the numerator and the denominator. But if we change it into this form, and then yeah, it will be just to compute it just once, right? Because this exponential term is involved only in the denominator, and usually e to the power of y or this kind of exponentiation is actually taking non-trivial amount of computation, and so we want to avoid this kind of computation as much as possible, right? Although in this particular case, we can also avoid this redundant computation in this manner. So maybe we just compute e to the power of y once and assign it as w, and then maybe um, w plus 1, w over w1 plus 1, okay? So if we just follow these two steps, and then, yeah, and then we can avoid the redundant computation of the e to the power of y, but yeah, we typically use this term because in these cases we have to require additional kind of memory or space so that we can store this temporary variable w. Okay, and additional computational tip when computing this sigmoid or the softmax as well is as follows. So yeah, that is more related to this softmax, but yeah, suppose we have this 5, 10, and negative 1, and then e to the power of 5, e to the power of 10, e to the power of 1, negative 1, and then this guy can become really, really large because this exponential function will have really sharp increase, right? And so in this case, what if this guy is becoming really, really large number that cannot be represented by our computer, right? And so in that case, yeah, in order to avoid this situation, we kind of do a little trick. So if we obtained this 5, 10, and negative 1, okay, and then we just subtract some constant value as maybe, let's maybe subtract maybe 10, and then it will be negative 5 and 0 and negative 11, and then let's just take the softmax function as follows, and then this guy's probability will be as follows, right? Okay, and then this guy is actually the same as this guy, right? Because we can just multiply e to the power of 10 both in the numerator and the denominator, and then we will get exactly the same representation as this, right? So if we subtract some constant value, and then the softmax output or result will not change, and thus in order to avoid this kind of overflow of some numbers due to this exponential functions, we usually subtract the maximum value from each of our each of our values, which will be the input to the softmax. Okay, and also one little notation. In this softmax is called the logit. Okay, so 5, 10, and -1 will be the input to the softmax, which will go through this kind of process, right? And those values will be called the logit. Okay, so so this logit has some mathematical root or some background that you can study, but I will skip that part. But those term called the logit is also used frequently in the deep learning libraries in such as Python or TensorFlow. So you can view this logit as the input to the softmax.